Okay, let me get this out of the way. All right, you guys. Hey, let's do some examples. You've learned everything you need to learn. Now it's time for you to do some examples. Okay? A 5 kilogram mass accelerates at 2 meters per second squared. What is the net force on it? Please do this problem now. I'll give you like 30 seconds. Okay, time's up. Net force equals MA. Net force equals, what'd you guys get? 10. But what's the units? 10 of what?
Newtons.
Well, it ends up being newtons, but what was it before newtons?
Kilograms times meters per second squared.
Thank you very much, Imani. That's exactly right. Because it's 5 kilograms multiplied by 2 meters per second squared. So the units are going to be kilogram meters per second squared. And you have to remember that. And if you don't remember that the units of newtons are kilogram meters per second squared, just remember that force is equal to mass times acceleration. Force is kilograms times meters per second squared. There's no reason for you to ever not be able to answer what are the units of newtons on an exam because you know the formula, MA. But anyway, as you guys know, we decided to honor Isaac Newton, and we don't like to write kilogram meters per second squared all the time. So we honored Isaac Newton and renamed that unit as newtons. So 10 newtons. But I do want you to know it's kilogram meters per second squared. Okay, you guys ready to do another one?
Yeah.
Good, that's what I like to hear. So here we go. Example number 2. This is a 5 kilogram box, and I am sliding this 5 kilogram box because I'm exerting 10 newtons of force on it. So that 5 kilogram box is sliding, but tell me, there's another force acting on this box that's opposing me. What is that force? Yeah, if you're thinking friction, you're right. The floor, friction from the floor. And let's say the floor is exerting 8 newtons of friction that opposes me. I'd like you to please find the acceleration of the box. What is the acceleration of that box? Net force equals MA. Write that down. Alrighty. Hey, are you guys getting that the net force is 2 newtons?
Yep.
So when you do net force equals MA, I got 2 newtons equals 5 kilograms times A. So are you guys getting 0.4 meters per second squared is A? Good. And please tell me, what's the direction of the acceleration? Is it to the left or to the right? How'd you know it's to the right? What's that? Good, the force is greater to the right. The net force is directed to the right, you see? So you would have to say 0.4 meters per second squared to the right, because you gotta give me the direction of your acceleration as well, alrighty? And that gets me to another fact about Newton's second law of motion. Not only does it give me numerically the relationship between force, mass, and acceleration, but it tells me something that's really, really important as well. And that is, whatever the direction of the net force is, that's the direction of the acceleration. You see that? That's the universe we live in. If I exert a force on this demo table that way, is the table going to run me over? No. Lucky for me, we live in a universe where that doesn't happen. We live in a universe where whatever the direction of the net force on an object is, that's the direction it accelerates. It doesn't have to be that way, but luckily that's our universe. So there we go. So I just want to write that down in words, okay? Where when I say the net force equals ma, this means that the direction of net force is the direction of the acceleration. Okay? They're always in the same direction, always, always. If I want something to accelerate in that direction, I better exert a force on it in that direction. So please do this problem. Let's say we are looking down on a couple of people pushing on a box, okay? And suppose this is a 5 kilogram box. And I've got one guy pushing to the right, or pushing to the left with 6 newtons of force, and another guy pushing down with 8 newtons of force. I'd like you to please find the acceleration, both magnitude and direction. Good luck. If anyone's stuck, I must tell you, you've got to find the vector sum of those forces. You need the net force, which means I'm going to put that force over here. And then I'm going to connect the initial point of the first vector with the resultant of the second vector. You know, you've got to find the resultant force. Then you can answer the questions. Alrighty. Hey, doing the Pythagorean theorem, what'd you guys get as the net force? Guys got 10 newtons, right? And so when I do net force equals ma, I got 10 newtons equals 5 kilograms times a. So I get my acceleration being 2 meters per second squared. How many people got 2 meters per second squared? Okay, yay for all of you guys. And let me ask you one more thing. What's the direction of the acceleration? Well, how many people say it's the same direction as the direction of the net force? Sure. So let's go ahead and find this angle there. What'd you guys get for that angle? 53.1. Good. 53 degrees approximately, 53.1 degrees. Yeah. And so I want you to see that since the net force is 53 degrees south of west, the acceleration is going to be 53 degrees south of west. 53 degrees south of west. Right? Whatever the direction of the net force is, that's the direction of the acceleration. That's the universe we live in. Any question or problem on this third example? Alrighty, then I need to tell you one more thing, and that's equilibrium.
Equilibrium.
I have a twin brother. I see him almost every day. He lives about 5 blocks away from me. He's a very important person in my life. When we were young, we fought almost every day. We fought. We were like itchy and scratchy. We fight. And so the person who would win the fight was the person who was most mad. Since we're twins, we were the same, strength and everything. And so usually the one who was most mad would chase after the other brother, and the other brother would have to run away. Now there was only one room in our house that had a locking doorknob, and that was the bathroom.
Okay.
Which means the one being chased would run to the bathroom and try to close the door and lock the doorknob before the angry brother could get to him, okay? And so the problem would come when here's the door and here's the brother on the inside of the bathroom trying to close the door, and here's the brother on the outside of the bathroom trying to open the door. And since we're equal strength, we exert the same force on this door. So let me ask you, since my brother and I are exerting the same force on this door, what's the net force on this door?
0.
Good, 0. So if the net force is 0, what's the acceleration of that door?
0.
0. And so what's that door doing? It's at rest. It's just staying there. So the door just stays there until one of us gives up or apologizes enough or whatever it takes. Okay? Well, this situation where the net force is 0 gets a special name. It's called equilibrium. Equilibrium. An object is in equilibrium when the net force on that object is 0. When net force on object is 0, then the object is in equilibrium because net force equals ma. An object at equilibrium has 0 acceleration. An object at equilibrium has an acceleration equal to 0. And so here's the last new thing I need to teach you. When an object is in equilibrium, that is, its acceleration is 0, there's actually 2 possibilities for its motion. 2 possibilities for the motion of an object at equilibrium. One of them we saw here with my brother and me. One choice is at rest. But what's the other choice?
In motion.
What's that, Mike?
I was told.
Okay, what is it? Yes, Chris?
Equal forces moving in opposite directions.
Okay, but I'm talking about the motion itself, not the forces. So how's this object, what other choice for the motion of an object is there if its acceleration is 0? Besides rest. Yes, Fatima? Sure, what kind of motion?
Constant velocity.
Sure, constant velocity. Remember, Newton's first law of motion gives you 2 scenarios, right? It says it says essentially an object will stay at rest or be at constant velocity motion unless there's a force impressed upon it, right? And so that's what's happening with equilibrium. Those are our 2 possibilities, at rest or at constant straight line motion. And I want you to always have in mind, whenever someone says something's at equilibrium or something has an acceleration of 0, there's 2 possibilities for its motion. And sometimes you can't even tell which it is. For example, in an elevator, has anyone ever had the experience of being in an elevator and not knowing if you were moving or not? Well, I don't know if you have. Okay, good. I have, because I go to Vegas all the time, and Vegas has really nice elevators. But sure, I know when I'm starting to move, because when it starts to go up, I feel heavier. And I know when I'm stopping, because when it comes to a stop, I feel lighter. But in between, when it's going at a constant velocity, when its acceleration is 0, if it's a particularly quiet elevator, I have no idea whether I'm at rest or not. I have to look at the numbers, and if the numbers are going ding, 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 then I know I'm in motion. You see? Let me give you another example. how about, has anyone ever been in like a train yard, like Union Station in Los Angeles? And have you ever been in a train and you look out the window and the train next to you is moving and you don't know whether it's them that's moving or you that's moving? Has anybody ever had that experience? Well, this is the same thing, because these both feel the same. If you're at equilibrium, there's no net force on you. You feel a certain way. But even though you feel a certain way, your motion could be one of these two things, and sometimes you don't even know which it is. But it could be either of them. See what I mean? So hey, that's equilibrium. And so what did you learn today? You learned F equals ma. You learned that it's the net force that matters. You learned that the acceleration is in the direction of the net force. And then finally you learned about equilibrium. And thank you very much for your patience and have a good day.